Welcome, my dear student, to Darasa Online. My name is Samuel John, a physics teacher from Baobab Secondary School. In our today's discussion, we'll be basing on rotational dynamics. This is a topic which is mainly found in mechanics, as you can see. So, in this topic, we are going to base on two items. One, we shall discuss about the parallel axis theorem and the perpendicular axis theorem. Why do we choose these two theorems? These are the two theorems that has difficulties to most of the students when solving some questions. So before we start looking at these two theorems, our first discussion will be on the moment of inertia. So I hope everybody knows about the moment of inertia of a body. When we talk of moment of inertia of a body, we talk about the axis of rotation. So moment of inertia of a body is defined when you know the axis from where that body is rotating. For example, this is our axis of rotation. And the particle having a mass m at a particular distance from this axis, that's r. We talk about a single particle. From there now, by definition, moment of inertia is defined as follows. This is for a single particle. But if you have several particles, which forms a body, now this is not the formula, but the formula will be in that way, my students, you can see, we know how to define the moment of inertia of a body. So when talking about the moment of inertia of a body, we have to see what are the factors that will make it to change. You can see from the definition, we have two items, mass of the body and the distance from that axis where that body is rotating. When we talk of the mass of the body as a factor number 1, when you have a small mass rotating from that axis, it means the moment of inertia will be small. By definition, when the distance decreases, the value also decreases. When you have the bigger mass of the particle rotating from the same axis, it makes the moment of inertia to be large. That's one. The moment of inertia depends on the mass of the particle. But it happened that not only the mass, but the factors which we can consider also. How are these masses distributed over the body? The factor number 2 is the distribution. Distribution of the masses. If there are several forces, so as several masses, distribution of the masses within that body. For example, let's take example of this. I've taken only these two masses as an example. Suppose a person is holding these two masses while standing on the table which rotates at a particular axis. This is the common examples that we normally see in our life. In most cases, you see in athletics, you see someone holding the masses while these masses are stretched away from the axis of rotation like this. Since the masses are very far from the axis here, when you are rotating, it means the value of the moment of inertia will also increase. When increasing the moment of inertia, it has connection with the speed. When the moment of inertia increases, the speed of rotation will decrease. So in order to increase your speed while we're rotating on the table, you should lower the mass. How? You bring the masses close to your chest, or this mass will be dropped down By bringing the mass close the chest, the axis of rotation, it means you are reducing. You are bringing the mass close to the axis. So by that definition, you can see when the distance decreases, when you bring the masses close the axis of rotation, you are trying to reduce the distance. As a result, the moment of inertia will decrease. When the moment of inertia decreases, the speed of rotation will increase. That's how someone who is standing on the table, which rotates, will make a quick rotation than someone who is stretching the masses. This one area where the moment of inertia can be applied. The second area, we know, you remember, in Olympic Games, we have those people who are diving from the high board. Before diving, we are given some condition that they're supposed to land on the surface of water surface. Now, there are some conditions which are set to choose the winner. They are making count on how many rotations you make in air before reaching the ground. So in order to make more rotation in air, you must have higher speed. The speed should be high. The speed should be high for that. How do you increase the speed of rotation? If you are experiencing the Olympic Games, you see most of the people who are diving from the board. The board, the legs and arms, and the legs, they're supposed to be close to the axis. They're putting the arms and legs inwards. By bringing your body close to the chest, the legs and the arms, that means you are reducing the moment of inertia. That means how the masses are distributed. By bringing them the distance from that axis, we make a decrease in the moment of inertia. As I said before, when the moment of inertia decreases, the speed of rotation will increase. So this is one of the areas where you can see the application of this moment of inertia in our life. So we have these two factors. But our today's discussion will be on the third factor, which is about the axis of rotation. And to start with, we have two theorems here, the parallel axis theorem and the perpendicular axis theorem. But before we start these two theorems, if you remember, in our previous discussion, we talked about the moment of inertia about a certain axis. I mentioned here about the axis that is known. And you derived the formula for finding moment of inertia about the center of mass. We have common figures that we know. So today in my class, I have brought some common figures which we're going to discuss about the formulas for finding the moment of inertia about the center of gravity. One of these figures is the grass rod. So you know how to find the moment of inertia of this figure. We said that this is the axis of rotation. This is the length of that rod. That is L. And this is the mass of that rod. So we derive the formula on how to find the moment of inertia of this particular body. If you remember, now this was the moment of inertia of this rod about the center of mass. That is 1. Second, we have another rigid body, which is called a circular disk. A circular disk, as you can see, when it rotates, it must have the axis. This axis is passing through the center. So you know the formula. I know you did this. The formula of a particular disk about the center of mass is given by a half m r squared. That is the radius. This is the formula you did in the previous, when you discussed about the introduction of the moment of inertia. Another rigid body is we call this a rectangular slab. The rectangular slab can be of this form. This is a book which represents a rectangular slab, which has the length, which has the width, and the thickness. And we derived the formula for this rectangular slab as follows. That's number 3. So this is the length, that is the width of this slab, and this is the mass of that rectangular slab. So these are the formulas that you did when deriving the moment of inertia about the center of gravity. Not only that, we have also another body which is given the name by a sphere. Moment of inertia of a sphere, a solid sphere, about its center of, we took geography, you know that when the Earth rotates, the Earth is also a sphere, spherical in shape. It rotates about its axis. So the moment of inertia of that sphere is 2/5 mr squared. R is the radius. So by these few formulas, we can see that the moment of inertia of a particular body must be determined from the axis at which that body rotates. So we discussed about this, and we derived the formula. I think everybody is comfortable on how to get these formulas. Now, our today's discussion is, suppose we are looking for the moment of inertia about another axis, which not necessarily passes through the center of gravity, center of mass. How do you find it? Maybe it's passing at the end. Maybe it's passing through the diameter. How do you find that? So that's our today's discussion. We're going to see how to apply perpendicular and parallel axis theorem when finding the moment of inertia of a particular body about another axis. So I know this is the areas where most of the students fail to answer the questions. Why? They fail to distinguish between the two axes theorem. Instead of using a parallel axis theorem, they apply perpendicular axis theorem interchangeably. And sometimes they get wrong answers because they don't have the proper knowledge on how to apply these two theorems. So after this lesson, everybody will be comfortable on how to apply these two theorems in a particular questions. And at the end, we'll be having some model questions on explaining on how to find these and how to use them in computing some of the given questions. At the end of the lesson, we have a chance to ask some questions from where you are and in sharing on how to use the two theorems. So to start with, we're going to start with the parallel axis theorem. So as I said before, our today's discussion will be based on the two theorems. Okay, let's start with the first theorem, which is talking about the parallel axis theorem. It's the theorem which has two words. From you can see, there are some words that has been given. These are in red color. These are the key lines which you are supposed to check in this theorem. These are the key points to be considered when discussing about this theorem. Now, the theorem says what? The moment of inertia of a body about any axis. About any axis. We are talking about, we said before, it was passing through the center. Now the question is, suppose it is not passing here. It is passing at the end, somewhere. How do you find that? So we are told this moment of inertia will be equal to the moment of inertia about an axis through its center of mass. So step number 1, you should know which parallel axis is passing through the center of mass. the parallel axis. Very important. Then you should know the two axes must be parallel. That you're looking about, they must be parallel. And when they are parallel, you should find the distance between them. So to show us this one, as example, think about this rod. I have this rod. This is the center. This is the moment of inertia about that center. We know the length here is L. This is the length of that rod here. Any length we choose. Now, suppose you are looking for the moment of inertia about any axis somewhere. You are told that we should know where is the moment of inertia about the center of mass here. Then we have another axis, maybe passing up at the end, one of the end. How do you see these two axes? The two axes are parallel to each other. So that's where the parallel axis should be applied. So it said the moment of inertia about any axis, about any, here, any axis must be equal to the moment of inertia about a parallel axis passing through the center. Yes, here, this is the parallel axis passing the center. Plus the product of the mass of the body, and the square of the perpendicular distance between the two. What is about that? This is the center of mass. This is the moment of inertia through the center of mass. This is another axis that I'm looking for. It's moment of inertia where that body is rotating. Now, this is the distance between the two axes. That distance should be perpendicular. Something like this. So you must have two parallel axes like that, not this way. One should be either vertical downwards, another one should be also like that. You can have two axes parallel like this, horizontal. So that's where you should apply parallel axis theory. But the point is that one of the two axes should be passing through the center. So the theorem says about what? Moment about that axis I equals to IG. Why IG? The formula says, the theorem, it should be the moment of inertia about the parallel axis through center, which is IG, plus the product of its mass of this object, m, d squared. So step number one, you should know whether the question is talking about parallel axis theorem. How do you know? You look at the two axes. Are they parallel to each other? If they are parallel, one of the two axes should be passing through the center of mass. Then it's easier to find that. For example, you know, moment of inertia at the center of this, as we said before, is given. Moment of inertia of this particular object was given as ml squared over 12 at the center. How do you find the moment of inertia at the end? So you take I equals to Ig, which is ml squared over 12, plus the product of the mass times the perpendicular distance. In this particular question, what is D? What is our D? Since that axis is passing through the middle, the D is taken at half of the length. So here, my dear students, D is L over 2. Comfortably, you know how to get that D. Then you plug in the formula here in our D squared. We get I equal ml squared 12 plus m L squared over 2. If you open the bracket there, simplify. This is m L squared over 12 plus ml squared over 4. Combining the two, we get ml squared over 3. Yes, we know it now. You might be given this moment of inertia at the end, and be asked to find the moment of inertia about the center. How? Check. Let's check. Suppose you are given this moment of inertia of a particular object, that body, about the end of that axis, at the end of the load, which is now given as I. Can we prove that the moment of inertia of this body about the center will be the same as that? In other way, the competence-based equations, you might be given the moment of inertia about the end and asked to find the moment of inertia about another axis, which is parallel to that, but this time is passing through the center of mass. Easy. You have to consider the same formula. You're looking for I. This time I is given. Is m L squared over 3 equals to Ig, assuming that we don't have this, plus our distance here is L over 2. The question is, are you getting the same answer? Let's check. M L squared over 3 equals to Ig. We're looking for this, M L squared over 4, making Ig the subject. It's ml squared over 3 minus ml squared over 4. The LCM between the two numbers is 12. 12 divided by this, 4. 12 divided by 4, 3 ml squared. And you can see you're getting the same answer. Wonderful. M L squared over 12. So it's very simple. As long as you know how to apply this theorem, you will enjoy that. This is one of a particular explanation. We can have different figures. Not only this, circular disk, sphere, ring. The principle is the same. Mind you, when you talk about the circular disk, as an example, number 2, we have the moment of inertia about the center. We know it. We might be looking for the moment of inertia about another axis, which is passing through its circumference, like this, but parallel. So the formula, the same. You know the moment of inertia about the center, we did before, is a half ml squared. And then the distance between the two, since this axis is passing through the center, this is the radius. So as you can see, you can be able to get the moment of inertia about another axis, which is passing through the circumference, but perpendicular to the plane. The problem here, to most of the students, about this part is, there's a problem here on this part. This is the disk, and we say this is the moment of inertia through its center. This is the center, this is the radius. Now we are looking for the moment of inertia at the end here. Now the problem here comes to most of the students. Since the question says, find the moment of inertia passing through the circumference, but it is perpendicular to the plane. You can see the word perpendicular means it makes 90 degrees here. When they hear the word perpendicular, they think this question is supposed to be using the perpendicular axis theorem. Perpendicular means the axis is passing like this. You may be given a question where the axis is passing parallel like that. So that's where you should know the key points. So here, perpendicular to the plane means it makes 90 to the plane, and hence the two axes are parallel. So applying the same formula, we have the moment of inertia about that axis is given by I said you can use H or D. So you are looking for the moment of inertia about an axis passing through at the end of this disk. So the problem here, since the two axes are parallel to each other, most of the students, they normally confuse, thinking that they are supposed to apply perpendicular axis theorem because this axis is perpendicular to the plane. The point to consider, the two axes are parallel. So the formula, we know moment of inertia of the disk about the center is a half mr squared. For this case, our h, the radius of the disk. So this I equals to a half mr squared plus mr squared. That gives us 3/2 mr squared. This is the moment of inertia of this at the disk about its axis, which is passing through the circumference, but perpendicular to the plane. I think now you are comfortable and you are aware on how to apply this parallel axis theorem. Now, our second theorem is the perpendicular axis theorem. Now, the theorem says the moment of inertia of a body about an axis perpendicular to the plane. You can see that word, perpendicular to the plane. That axis should be perpendicular to the plane. So the key point here, that axis you're looking about, you're looking for, it should be perpendicular to the plane, according to the theorem, is equal to the sum of the moments of inertia of a body about any two perpendicular axes in the plane, but this time they must intersect the first axis. It's very difficult to see that theory, but let's see what this means. The theorem says that, suppose we have an object, a disk, this is that is the axis which is perpendicular to the plane. Like here, that IZ is this axis here. This axis is what you call the axis passing through the center of gravity, which is given the name, the axis through Z. Now we have another axis which is passing like this. That axis we call as, because it's something, it can be either X or Y. That is one of the axes. Then we have another axis passing like that. So there are two axes. These two axes, they are laying on the horizontal line. But you can see this axis, which is along the Z, is intersecting the two axes. So the theorem says you should know which axis is perpendicular to the plane. It is this IZ. Then we have this, maybe it's a moment of inertia about the axis, which is given the name maybe X. Another axis which is given the name Y. So if you draw this diagram, let's choose this to be X, this to be Y. Now the two axes are, these two axes are perpendicular to each other. So the formula says the theorem, moment of inertia about the axis which is perpendicular to the plane. As we see, it is Z here. So IZ equals to the summation, the sum, IX plus IY. The point to know, this moment of inertia about the center is the one we talked about, the moment of inertia about the, it can be the center of gravity. Sometimes not necessary, it can be somewhere at the end. So it is the moment of inertia which gives us the sum of the two. Because this axis is perpendicular to the plane first, but these two axes, as you can see, they are parallel, they are perpendicular, but they're intersecting that. So the conditions, number one, that axis which is passing to the plane, which is part of the perpendicular to the plane, should be equal to the sum of the moment of inertia of the two axes, which are perpendicular to each other, but they must intersect the first one. Now, it's very difficult to see, but if you look for a disk like this, we know that the moment of inertia about this diameter here, this is the diameter. The moment of inertia, this is the x, or this is y. So the diameter, it divides the cycle, this plane into two halves. Moment of inertia about this is the same as the moment of inertia about, because the diameter, at any point you choose, is the diameter. So moment of inertia about any axis which is given the name of the diameter will be the same. So we say moment of inertia about x. This is for a disk. Other objects will be determined by adding them. For a disk, we say the moment of inertia about x equals the moment of inertia about y, because the two axes, they are dividing the plane into two halves. And we have the moment of inertia about z equals to 2ix. And this is the moment of inertia about the center, which we have. Knowing the moment of inertia about the center of gravity, we can find the moment of inertia about its diameter. That's one area where you can apply that perpendicular axis theorem. Another area is this. You have the same disk. The moment of inertia about the diameter is given. The moment of inertia about its end here, it's passing at the end here. We know. Maybe you are given the moment of inertia about the same disk about the diameter. And we are looking at the moment of inertia which is passing through the circumference, but this time it's parallel like that. Provided that the moment of inertia passing through that point, intersecting the two, and perpendicular to the plane is known. So that will be our z, Iz. So Iz equals to the sum of the two axes. So the perpendicular axis theorem, it applies only when you have two axes which are like this. They are intersecting. And you have another axis which is perpendicular to both. And we saw it can be applied at the center. We have two at the center. And this time, this is acting as the moment of inertia through the z, which is given the name the center of gravity. So that is the areas where most of the students normally confuse, where to apply perpendicular axis theorem. I hope you have understood where and how to apply the two theorems. Let's go back now to the questions. Example number 1, you are given a question. This is the competence-based question. We don't expect to have a direct question, so you should know how do we compute the two theorems using the competence-based question. The question says, a student immersed a uniform copper rod of radius 2, density 9,000 kilograms per meter cubic into a certain liquid. The liquid is not given. And after immersing in that liquid, he found that law, it loses 10% of its mass. We know from the principle of Archimedes' principle on the law of rotation, when a body is immersed in the liquid, it loses some weight and mass also. So we are told how much mass has been wasted. Now, if the length of the copper is given. Now the question is, very interesting, calculate the moment of inertia of the rod about an axis passing through one end. So step number 1, you should think about how do you find the formula? The formula for that moment of inertia which passing through one of the ends and perpendicular to the plane. Let's draw the diagram. Step number 1, for this question, you should know how to draw a well-labeled diagram. So here we have our rod, copper, whose dimensions are given. We know this is the center of mass. But this time you're looking for the moment of inertia of the same load about an axis, which is passing through one end and perpendicular to the plane. Mind you, that particular load y is still in liquid. So the quantities are given, the formula we might be using, you should know that you're supposed to find the mass of that object when in liquid. So step number one, let's find the moment of inertia at that particular axis. We call this as I, rotating. We know that is our h. Step number one, the formula. The two axes are parallel axes. The two axes are supposed to be parallel. So we are supposed to apply the parallel axis theorem. We are sure that's where the parallel axis will be applied. So I equals to Ig plus mh squared. That m is the mass of the liquid. Is the mass of the object when immersed in that liquid. We should know. And at the end, we should find that mass. So we know the moment of inertia of the center. Maybe not changing, not thought, is given by m L squared over 12 plus m. Our h is a half of this length. Since this is passing through the center, our h is half. So it's L over 2, half of the whole length. And we get ml squared over 12 plus ml squared over 4. When simplifying, we get ml squared over 3. That is question number 1. We know the moment of inertia about that axis. The problem is, where do we get the mass? That is the question. And we know that the mass of that rod, when immersed in a liquid, it loses 10% of its mass. Let's find the mass of the rod copper before immersed in that liquid. It means the mass of the rod in air. Ma is given by the density times the volume, by definition. We know that the density is given. How do you find the volume? Volume, because it's a rod like this, you can find the volume if you know this area times the length. So the volume is given by area times length, which is pi r squared L. So this gives us Ma equals to density times pi r squared L. And the density is given, so make sure that you have your calculator. I have mine. The density of that load is given as 9,000 times pi, which is found in your calculator, times the radius, which is 2 converted into meter, 0.2 squared, and the length 0.4. Compute that to get something like 9,000 you get something like 4.5. Check correctly your answers to get that value. This is mass of the copper in air. And you are told it loses 10% of it. So mass L now in the liquid is given by, you take Ma minus 10%, which is 0.1. 10% times Ma. 10% of that, it means Ma minus that is almost 0.9. 0.9 Ma. So you know how to find the mass of the liquid. You substitute that 0.9, and you get 4.06. If you use your calculator, you get that value. So this is the mass of the liquid and that particular copper rod when you immerse it in it. So you know the mass. You know that mass is the question number 2. You substitute these values in that formula, meaning that you know the length of copper rod. So from there, you get the moment of inertia about that axis as 4.068 times 0.4, the length squared over 3. You get something like 0.22 kilogram meter squared. That question was very interesting. After knowing the formula for competence-based question, it's not the matter of ending there. You are supposed to know some areas where some of the principles must be applied, like where you applied the Archimedes principle here to determine the mass. Okay, so I'm going to see in part B, but you might be given how much mass has been left, where you can use that concept to find the moment of inertia. The second part, very interesting. What will be the new moment of inertia of the same rod about the same axis when it is measured in another liquid of density, which is 1,200 kilogram per meter cubic? So you are looking for the same moment of inertia of the same particle, which is passing about the same axis. But this time, it is measured in another liquid whose density is different from this. So from the from the Archimedes principle, what you know, the formula will be the same. The formula will be the same, but we know that the mass of the liquid which has been displaced, part B, mass of the liquid has been, we talk of the mass of the liquid displaced. That is the mass of the solid. Mass of the solid now, which is only measured in that, which we talk about that, equals to the density of the liquid times its volume. So the mass of the solid in that liquid will be equal to the volume of that liquid, according to the Archimedes principle, times its volume. So from there, you can find the density is given as 1,200 times the new volume. So you know the volume is pi r squared length. So we have that, and the radius is 0.02 squared times 0.4. So from there, you get the mass of the solid when immersed in that liquid. And if you compute that, you get that mass as 0.6 kg. So you apply in that formula. You get the moment of inertia about that axis equals to 0.032 kilogram meter squared. So the moment of inertia will change depending on a particular question. When that body is immersed in a density of 10,000 kilogram per meter cubic, we got different values. When it is immersed in another density of 1,200 kilogram per meter cubic, the moment of inertia will change. So this shows that the moment of inertia of a particular body is not unique. It depends on several factors, as we discussed. I think you have understood that question. This is one of the areas where now the question is asking to find the moment of inertia at a particular axis. That axis is given. You might be given a very challenging question where the moment of inertia is supposed to be found at a certain axis, which is not known. Let's see example number 2. Example number 2, a group of students who did an experiment to determine the moment of inertia of a particular disk of diameter d and the mass m. And we don't know the axis of rotation. We are told they did an experiment to determine its moment of inertia. And they found to be 3/8 md squared. Now the question is, establish the axis of rotation which produces the above moment of inertia. In other words, you should explain by calculations and come up with a conclusion to tell us where was the axis of rotation of that particular object. That question is very difficult if you don't know how to use the theorems. But that question is very easy when you know how to use the theorem. It is in a way around, you are supposed to be given questions to use the parallel and the perpendicular axis theorem. Let's see the question together. Now the question is talking about a disk. Yes. If it's a disk, you draw the diagram for a disk first. A disk. We know the answer. You are given the moment of inertia about a certain axis is 3/8 md squared. The question is, where is that axis? Through the center, through the diameter, through the circumference? We don't know. So step number 1, where do we start? Can we find it at the center? Let's check. We know we are looking for the moment of inertia, which is given. It's supposed to be md squared over 8. Now, which axis? This is the moment of inertia which is given, g. Let's use the small g, given. Now, which axis is that g? Is it the center, diameter, whatever? So let's start step number 1. Let's find out, is it passing through the center? The center of this disk, we know the formula is I equals to m r squared, where r is the radius. So we know the radius and the diameter, they are related by that. Diameter is 2r. Let's check whether this moment of inertia, which is given, and if you get the same answer, it means that object was rotating about the center of gravity. So if you take r as d over 2, we get equals to 1/2 m d over 2 squared, which gives us m d squared over 4, which is 8 about the center. Are we getting the same answer? No, that's not correct answer. It's not passing through the center of gravity. We go to another alternative. If it's not passing through the center, can we check? Is it passing through the diameter? Let's check. Case number 2. Maybe through the diameter. Let's check. If you know the moment of inertia about the center, we know, and you can find the moment of inertia about the diameter. As we did before, if you remember, we said the Iz equals 2Ix. That x stands for the moment of inertia about the diameter. So we know that z, which is Iz, is given as m d squared over 8, moment of inertia about the center. This giving us 2Ix. Let's check whether it's passing through the diameter. Dividing by 2, we have Ix equals to md squared over 16. Question number 2. It's not correct. That body is not rotating about the diameter. Very challenging question. So we're supposed to keep on moving, finding the maybe to look for another alternative. We have tried the axis through the diameter, we failed. The center, we have failed. Let's look for, suppose it's passing through the circumference like this, but this time it is parallel to the axis to the plane. Suppose it's passing through the axis like that. So if it's passing through the circumference of the disk, but parallel, which theory do you apply? We know at the center, the formula for the center is given. The moment of inertia about this now, this may be passing through the center, but it's the diameter. And this is the axis passing through circumference. Since we know this, we can find the moment of inertia about that axis. The two theorems, the two axes are parallel. So you apply the parallel axis theorem. Let's check whether it's passing through this axis, which is touching the circumference and parallel to the plane. That's case number 3. We know that the moment of inertia about that axis here equals the moment of inertia about the center plus the product of the two of the md squared. It's now, what is our center here? Moment of inertia about the center is not the center of gravity. This time, the moment of inertia about the center, this time is the diameter, d plus md squared. About the diameter, which is x now, is given by md squared over 16 plus m. Our distance between the two axes is the radius. And we know the radius is d over 2. So it's d over 2 squared. The distance, our d here is r, the radius. And this d is not confusing maybe. You can use maybe h, not confuse. That h is the distance between the two axes, which now, according to this question, this equals to r. If you find r in terms of d, since the question consists of d and m, so we come up with the md squared over 16 plus md squared over 4. If you find the LCM is 16, get md squared. 16 divided by 4, get 4. So the answer is about that axis equals to 5 md squared over 16. Question number 3. Wrong. Not the answer. It's not passing there. This is md squared, 3md squared over 3. So where is the axis of that body? We have tried at the center. We have tried through the diameter. We have tried through the circumference and perpendicular to the plane. We have tried. So you are maybe the last alternative. Maybe you can find it's passing through the circumference like this, perpendicular to the plane. Okay, if this is the case, this axis will be parallel. This is the last option. It may be passing through the circumference like this of the plane and perpendicular to it. Okay, if this is the case, this axis will be parallel to the one which is passing through the center. Let's try to check whether this body was rotating about that. Very simple. Case number 4. We have now moment of inertia about that axis. Let's take B equals to moment of inertia about the center plus mh squared. And we said our center here is given, which you know now, md squared over 8. We're looking for that. Check whether this is the proper axis of that body. So our IG is given, which is md squared of 8 plus our h is the radius, which is given by d over 2 squared. This equals to md squared of 8 plus md squared over 4. If you combine the LCM here, it's 8, here is b md squared. 8 divided by 4 get 2 md squared. And the answer is 3 md squared. So now the answer is, the question was given in a single line. Establish the axis of rotation which produces the above moment of inertia. On a single line. But you can see how many steps do you apply. Step number 1, step number 2, step number 3, step number 4. We applied both theorems, parallel, perpendicular axis system, to check at the last we found that that object was rotating about an axis which is passing through the circumference of the disk, but perpendicular to the plane. This is the answer. It's passing through the circumference and perpendicular to the plane. That's how the moment of inertia could be used in a particular moment, to find the moment of inertia at a particular axis by using parallel and perpendicular axis theorem. So I hope you have enjoyed to know how you can apply correctly the use of parallel and perpendicular axis theorem we have seen two examples which give us the competence-based questions that you may be given in any exams. So that comfortability will make someone to be comfortable now when solving any question relating about that. We have a short break and we'll be back. We are back from the short break. So we received some comments and messages from the students. I'm reading some of the messages I received from them. One is from Irene Joel from Kigoma, from 6 PCB, said, it has been a nice presentation because it had difficulties on how to use the two theorems. Thank you for a nice presentation. That's a comment. Keep on touch. We get more from here. The second is from Abdul Hamis from Zanzibar, who say, greetings, sir. Thank you for a nice presentation, but when are you presenting on the magnetism? Because it is another subtopic, not a subtopic, which gives us difficulties when solving some question. Okay, don't worry. Keep in touch with the programs, class online. We know most of the questions that will be coming.